Good morning, everyone. Thanks for being here. We really appreciate it. I am Alex Cook. I've been an Island School faculty member and tied to this CSD in some way, shape, or form for the past 3 years. I've co-managed the bike shed. I've advised human ecology projects. I volunteered over there. And I'm really passionate about the CSD. And I've been a research advisor for the Pyrolysis team for the past year. Thanks again for being here.
Good morning, everyone. My name is Sarah Emmerich. I'm an engineer and research advisor at CSD, working on sustainability projects and research and waste-to-energy initiatives.
Hello, everybody. My name is Alex Perkins. I'm also an engineer and research advisor at CSD. I work with Sarah on a lot of the same initiatives, and our team's really excited to share our progress in those fields with you this semester.
Okay. Hi, everybody. Thank you for coming. We're the Plastic Pyrolysis Research Team, and we're really excited to share our presentation. I'm Sibley Dickinson.
I'm Jack Johnston.
I'm Troy Markison.
I'm Danny Muhammad.
I'm Henry Howe.
I'm Jarrett Young.
And I'm Ellie Felderman.
So what we're going to talk to you guys about today is a little overview on this plastic crisis that we're in, how we're trying to solve it here at the Island School, some information on our design and what we've been doing as a team, and a little bit of analysis of our results and what we want to do in the future. Oop. So this is a waste management hierarchy. The first three are the three best things you can do to minimize your waste production, and that's what we can do at home. Recycling is pretty self-explanatory. Energy recovery, that's taking waste and turning it into fuel. So in our case, that's pyrolysis. And disposal, that's putting your waste in a landfill. So right now, most of the waste that we have on Eleuthera and on remote locations is in these landfills. So this is in Tarpon Bay. And when the volume of the waste gets too high, they burn it. And the burning of plastics emits greenhouse gases such as dioxins. Dioxins are 10,000 times more toxic than carbon dioxide. So this is a landfill in Nassau. This is actually an accidental fire, but it kind of just goes to show the unsafeness of these fires, and they actually do burn the waste too to get rid of the volume. And schools are closed because the fumes are so bad. Kids can't go outside. So going back to this waste management hierarchy, we don't have the infrastructure on Eleuthera for a proper recycling facility. So the nearest one is in Nassau, and shipping your recyclables to Nassau emits a lot of carbon dioxide and emissions, plus it costs a lot of money, so most people don't recycle. So the more sustainable way to go is pyrolysis or some form of energy recovery. So yeah.
So this is sort of the lifespan process of what we have here at the Island School for Plastic. So at first, oil is drilled from the ground, it is extracted, and then it is shipped to a refinery where it is turned into plastic. Once it is plastics, it's shipped here to the Island School, we use it, and then as soon as we use it, it's waste and there's no other use for it. And our job through pyrolysis is turning it back into fuel. So it gives it another chance to have a life. So there's 7 different types of plastics. These are the 6 most common. So type 1 is the disposable water bottle, the plastic water bottle. Type 2 is bleach containers and milk jugs. Type 3 is PVC piping. Type 4 is bottle caps, such as a water bottle cap. And type 5 is Tupperware, such as a yogurt container. And type 6 is a very light polypropylene, such as styrofoam. Raise your hand if you know you are wearing plastic or have plastic on you right now. If you're wearing shoes, you should probably raise your hand. Know that this plastic is going to be here for the next thousands and thousands of years.
So, pyrolysis is the thermal decomposition of a material with high heat and low oxygen. In our situation, we are using plastic to create a synthetic fuel similar to diesel. So, as you can see here, as Sibley said, plastic can go to a landfill and be burned and emitted as dioxins. It can go to a recycling center, but it can be recycled about 3 times until it's degraded and has to go to a landfill and be burned. Or we can try and use pyrolysis to revert it to a synthetic fuel. So we are cracking the hydrocarbon chains that holds plastic together and reverting it back into its fossil fuel form. And there are 3 products of pyrolysis. There is a 3 to 5% char, there is about 10% non-condensable gases such as methane, and the rest is our synthetic fuel similar to diesel. So synthetic fuel at the Island School would mainly be used in our small machines and vans around campus. We generate 5,000 pounds of plastic waste every year. And all of this is just sitting in our resource area right on campus. And the main goal of pyrolysis is to get rid of this plastic waste. And this goes along with the main goal of the Island School and the Greater Cape Eleuthera Foundation to become a zero waste campus. So in the past, synthetic fuel has been used in conjunction with biodiesel at a 25-75% ratio. And every time you use synthetic fuel for anything, you're offsetting the diesel that would need to be produced or the biodiesel that would need to be produced, and all of that plastic is eventually being used. Because again, we're not trying to find a fuel alternative, because biodiesel can produce 10,000 gallons of plastic every year, which is a lot more than with the amount of plastic we can produce. It's to get rid of all this plastic waste, which is just literally energy that's just sitting in the ground.
So after 80 days of hard work, this is the system we've built. This is not something you can buy at Home Depot. This is something that has taken a lot of design and construction to make. So we start in this tank. There's a reaction vessel. We put all the plastic in the reaction vessel and we seal it so there's like minimal oxygen in there. We have a propane heat source that heats up the tank, heats up the reaction vessel, vaporizing the plastic up this pipe into this condenser. Within the condenser, water surrounds the plastic gas, condensing it into an oil in this collection vessel. This is a big water tank with a pump in it. The oil collects in here. While there are some non-condensable gases, they go through this pipe into this bubbler. We have to remove them from our system using a flare at the top to burn them off. Burning them out as a small amount of CO2, though, is far better than leaving them in a landfill where they would be released as methane, which is 27 times worse than CO2, or dioxin, which are 10,000 times worse than CO2.
So last term created a small lab-scale system that proved that pyrolysis worked. They were successfully able to pyrolyze approximately 100 grams of shredded plastic waste and yielded approximately 60 to 80 milliliters of synthetic fuel per batch. This term, we are looking to take approximately 60 pounds of our plastic waste here on campus, which is in our recycling center, put it in our brand new shredder and our bigger reaction vessel to hopefully yield approximately 5.7 gallons of synthetic fuel per batch. So as Danny mentioned, we have a bunch of system improvements. Here we have our condenser, which condenses the gases. We have a brand new heat source, which allows us to control the temperature of our system at all times. And we have our flare here, which burns off the non-condensable gases. The process. So as Danny mentioned, we created the system from scratch without any instructions. On a daily basis, we do a lot of metalworking, such as angle grinding, pipe threading, drilling, and welding. But don't worry, Mom. We are completely safe throughout our process, as we wear respiratory masks, gloves, jackets, and goggles as we are creating our system.
All right, we have 2 pictures here, and on our left, we can see a rendered picture of our system, and on the right, we have a final picture of our working model. We, at first, in the beginning of the semester, we hope to have the final look like this, but over the semester, we've ran into a couple different obstacles because we started from scratch without any instructions. During some obstacles that we ran into, an example of that is on our reaction vessel over here, we needed a gasket for the reaction vessel, and instead of purchasing one for about $200, we created one for free from our repurposed waste in our recycling center. So from our final working model, we hope to gain replicable data, pyrolyze our weekly waste on campus, and to gain some synthetic fuel from our experiments.
So one of the things our team is looking at are the calorific values of the process. We want to make sure that we're getting more value and energy and money and fuel out of pyrolysis than we're putting into it. And so that means looking at how much propane we're buying, how much we're using to fuel the reaction, and the synthetic fuel we're actually getting out of it. We know that there's a theoretic 4,000% energy conversion rate. I'm going to say that again because it's a really big number. 4,000%. We can put 1 unit of energy into our process and get 40 units of energy out. And another part of our research process is looking at how close we can get to that 4,000% conversion rate. We know that if we run the pyrolyzer twice a week, we can both deal with our weekly waste on campus and the pyrolyzer will pay itself off in 2 years. We can run half of a van for an entire year with the amount of plastic waste we produce annually. There are a lot of different directions our research could go in the future, and the way we've designed and built and set up our system is so that we don't need to change anything to test things like different plastics, different temperatures, different rates. We'd like to add a lot of things to our system and make a lot of upgrades, and one of those things is a way to automate the process more. Instead of doing what we're doing presently, which means that someone has to set up the process and monitor it all the way through, we'd like to find different ways that we can automate the process more so someone can set it up, get it going, and come back when the reaction is complete. As Chip said, we are moving towards being a zero-waste campus, and some more ways that our project can contribute to that are both by getting a toxicology report on the char that's left over at the end to see if it's safe to bury it in the soil at the farm as a soil amendment, and to see if there's a way to pipe those non-condensable gases back into the front of our system, feed two birds with one worm, both getting rid of our emissions and getting a heat source from a byproduct of our reaction. Another thing that we're looking at is getting a lab analysis of the fuel that we're producing. We can test flammability, viscosity, and density on campus currently, but we'd really like to be able to send a more consistent yield of our fuel out for further analysis to know exactly what we're getting out of pyrolysis. One of our broader, more long-term goals as a research team is once we have pyrolysis working well for the Island School, is to take ourselves as a model and spread it to the greater community, to Eleuthera, to the Bahamas, to remote locations everywhere so that they can also have a better way of dealing with their plastic waste. If anybody's interested in seeing our system, we're going to have it set up over here at the other side of Boathouse Cut after lunch. Our research advisors are going to be there, and you can take a better look at it in between your meetings so you can see what we've been working on all semester in real life. Here's our literature cited. We'd like to thank the following people for their help and support on our project. Does anybody have any questions?
About Nassau, how much recycling do they do, and has there been any talk of introducing this type of system over there, because they're really exploding in their population and their building and kind of making it seems like their resources will become very limited quickly.
So the question was about Nassau and how much recycling they might be doing, and if pyrolysis has been a solution that's been talked about or introduced over there. So currently, the closest recycling facility is on Florida, and that's what we were talking about earlier with all of, there's no infrastructure for that here, and so all of the recycling needs to be shipped to Florida, which gives off more emissions, which costs money. Like, you have to pay yourself to send your recycling somewhere, which really doesn't give people much incentive to actually recycle in the first place. And so there are some very large-scale commercial corporations or people doing pyrolysis on a large basis, but there really isn't that much information about it. No one's doing it on the same scale and in the same capacity that we're doing for here. And so the really exciting thing about this is that we can actually take this and introduce this as a solution for places like Nassau and other places that have a really hard time dealing with their plastic waste.
Does part of your research include scale? So the question is, if you were to scale the system out to something large enough to support the entire island, say, is it something that's would create a situation where you have to put more energy in the front end and you get less product out of the back end, or does it scale in a linear fashion?
Right, so the question is about scale, is if we can take this model and increase in size or decrease in size as needed for different communities.
So the system, the 1 to 40 energy increase, or the 4,000% increase, is a calorific value. So any amount of plastic, you have a certain amount of fuel that you would need it to put in to thermally decompose the plastic, and you will get 40 times that of energy out. So the way this could be scaled, if you wanted to scale and have, let's say, one pyrolyzing facility for Luther, or maybe one for each settlement, it can be scaled to your exact specifications. We, the last term, found out how much plastic waste we generate, and so we, with knowing that we want to run it twice a week, we found out the exact size vessel that we would need to run our plastic waste generated every week, yeah.
That contraption looked dangerous. So my question is, when you first fired it up, were you guys like hiding behind a wall? You got it compressed in that barrel, like let's see what happens, or how did that work?
So the question is sort of essentially if it's like a safe process. Somebody wants to answer that, or I can answer it.
Yes, it's actually a very safe process. It's actually an open system, so what that means is there's no pressure buildup. So every part of the system is at atmospheric pressure, because our non-condensable gases can escape, but since it's in water, no oxygen can come back in the system. So there is no pressure buildup. And also, we're being very safe with what types of plastics we use. We're using type 3 plastic. We are not using type 3 plastic, sorry, because it gives off a chloride gas, which is very harmful to us. And we are not using type 1. This is not really for safety, but this will type 1 contains benzoic acid, which degrades the fuel quality. So those two plastics can be pyrolyzed, but we do not do that just for our safety.
And over time, with a more, let's say our system was taken commercially and it's run in the States or in Nassau, we have an actual commercial facility, they can pyrolyze, most likely we'll be able to pyrolyze those types of plastic because they'll have safety equipment for not breathing in the chloride gas, and they'll possibly be able to remove that benzoic acid. And in our case, eventually we probably will use number 1 plastic that contains benzoic acid, and just like the non-condensable gases that at the moment we're burning off, we can just run that back through the system instead of propane to just really even increase our energy conversion rate.
Well, I'm just wondering, are you the first and only research facility doing this, or is this being done elsewhere in the country or in the world?
So the question was if we are the first that are doing this, or has it been done in other places around the world?
So we're not the first people to do pyrolysis ever. There has been pretty minimal research done on it in other facilities and by other researchers, and we've had a few resources that we've used to help us with it. That's how we know the 4,000% energy conversion rate, because other people have done research on that and have found that number for us. But we're definitely the first to be doing it on this scale and in this capacity. Like I said before, there have been a few commercial pyrolysis systems, but information coming from them is very limited. It's being kept very close to their own corporation. So the vast majority of the work we've done here has been coming from our own research, our own experience, and everything that we've run into while we're building this system. And we designed this system specifically to deal with the island school's waste stream. So everything here is coming basically entirely from us.
So the commercial pyrolyzing systems that were mentioned, as she said, those companies generally withhold their information to monopolize the industry. So, ridiculous. So rather than, use their system and get rid of the plastic waste, like we're trying to do, and actually, really help the world, people like money. So that's what they're focusing on.
What that you have generated, have you tested it?
So he asked if the synthetic fuel has been tested.
So our product that we've created is diesel, and we know it because of the density of it, but we have not really gotten the chance to test it. When we do test it, we will test it mixed with biodiesel, as Tripp said. But last semester's research group built a small scale pyrolyzer to see if it worked, and they tested it, and it did work.
Also, the whole point of our research project was to build this machine, was to get it working, was to set the entire thing up. And we were really excited when we got those. We did 2 runs with biochar and we did 2 runs with plastic. And we got all the way through, the whole system worked, and we were really excited about that because it was sort of like extra, it was like a little bit of a bonus because we got the system done and then we got to actually test it. So we aren't at a point now where we're running twice a week and getting rid of all of our plastic, but we're at a point now where we can move to that because the system is done.